All right, everybody, and welcome back to Applications of Derivatives. So for this next section for curve sketching, what we're going to do is we are going to pull together everything that we have covered about what the first derivative can tell us about the graph of a function and what the second derivative can tell us about the graph of a function, and kind of put it all together to actually sketch the graph of a function without even touching a graphing calculator. So this is just a summary of what derivatives can tell us about the graph of a function. Remember, the first derivative is tied directly to where the function is increasing and decreasing, and the second derivative is tied to whether the function is concave up or concave down. So if the first derivative is positive, the function is decreasing. If the first derivative is negative, the function is decreasing. If the first derivative changes signs from positive to negative, you have a local maximum. If the first derivative changes signs from negative to positive, you have a local minimum. And at a local maximum, the second derivative is negative because it is concave down. At a local minimum, the second derivative is positive because it is concave up. So if the second derivative is positive, the function is concave up. If the second derivative is negative, the function is concave down. And at any point where concavity switches, you have an inflection point. So if the second derivative changes signs from either positive to negative or negative to positive, you have an inflection point. So curve sketching can be broken down into these 8-9 basic steps. So whenever you are sketching the curve of a function, you have to always remember the domain of the function or the interval of interest. So you should always start by identifying what is the domain of the function, because any point that is excluded from the domain cannot be a critical point, it cannot be a potential inflection point. So if a point that is not in the domain does come up as a critical point, you get to ignore it. And if it comes up as a potential inflection point, you get to ignore it. So always figure out what the domain of the function is and whether there are any points that are excluded. Now, what you can do, and I'm not requiring this, is that you can take advantage of symmetry if there is any. So if you plug negative x into the function and simplify it and you get the exact same function back, it is an even function and it has y-axis symmetry. If you plug negative x in for your x and simplify it and all of the signs change, you have an odd function which has origin symmetry. Now, whether or not you exploit symmetry is up to you. What you do have to start with is finding the first and the second derivatives. So the first and the second derivatives will tell you a lot about the function, so you need to find them first. Then you're going to find the critical points by figuring out where the first derivative is either equal to 0 or where this first derivative is undefined. Then you're going to find the possible inflection points by finding the second derivative and setting it equal to 0, or figuring out where the second derivative is undefined. Next, you're going to draw two number lines, one to represent the first derivative and one to represent the second derivative. On the number line that represents the first derivative, you're going to put your critical points on your number line and plug in test points to figure out where the intervals on which the function is increasing and decreasing. And while you're at it, you will use the first derivative test in that process to figure out whether those critical points are local minimums, local maximums, or neither. Then on the number line for the second derivative, you are going to put your possible inflection points on that number line and use test points to figure out where the function is concave up and where it is concave down. And in the process, you will also figure out where the inflection points actually are. Now, this next step is not going to be necessary for every single function, but if you do have a rational function which contains variables in the denominator, you do have to think about the potential for asymptotes. And we covered these back in chapter 2. So vertical asymptotes occur where the denominator equals 0, and if the limit as x approaches that number equals negative infinity or positive infinity. Then you find the horizontal asymptote by taking the limit as x approaches positive infinity and as x approaches negative infinity. That will also determine the end behavior in the process, as well as determining your horizontal asymptotes if there are any. Next, this part involves absolutely no calculus. A graph is not complete unless you have shown all of the x-intercepts and the y-intercept on the graph. So you actually need to go find the x and the y-intercepts. You find the y-intercept by plugging 0 in for x. Then you find the x-intercepts by taking the original function, setting it equal to 0, and solving for x. Then what you're going to do is you are going to draw a very approximate graph. I am not looking for a masterpiece here, but you're going to draw a approximate graph. Now, every single one of these points, all of your critical points, all of your inflection points, x and y intercepts, they all need y coordinates to go with them. To find the y coordinate that goes with a given x coordinate, you're going to plug that x coordinate back into the original function. The original function is what is used for y coordinates, not derivatives, not second derivatives. The original function is used for y coordinates. You're going to put them on the graph, and then using a combination of where is it increasing and decreasing, where is it concave up and down, where's your mins and maxes, you're going to then figure out the graph and you're going to draw an approximation. So we're going to take this function here, and without a graphing calculator, we are going to graph it on its entire domain. So first we need to figure out what the domain is. This is a polynomial, so your domain is all real numbers, which means there are no points that are excluded from the domain, so we need to keep that in mind. Also, if you want to rewrite this as 1/3 x cubed minus 400x, you may do so because it'll probably make finding your derivatives a little bit easier. So next what we're going to do is we're going to jump into finding the first derivative and the second derivative. So let's start with the first derivative. The derivative of 1/3 x cubed is going to be x squared. Derivative of minus 400x is minus 400. Then for the second derivative, you are going to take the derivative of the derivative. So the second derivative is going to be 2x. Then let's find the critical points. The critical points occur where either the first derivative is equal to 0 or where the first derivative is undefined. Since the first derivative is a polynomial, we just have to worry about where the first derivative equals 0. So I'm going to take x squared minus 400. I'm going to set it equal to 0, and I'm going to solve for x. So when you take x squared minus 400, add 400 to both sides, take the square root of both sides, and you get two critical points. You get x equals 20 and x equals negative 20. Then what we're going to do is we are going to draw a number line to represent the first derivative. And I'm going to make sure I label it as f prime. Positive infinity is here on the right, and then negative infinity is here on the left. And we're going to put our two critical points in numeric order on this number line. So negative 20 is going to go first, and then positive 20 is going to go second. And then we're going to plug test points into each of these subintervals to figure out where the function is increasing and where the function is decreasing. So we have the interval from negative infinity to negative 20. Pick a test point, any test point that's not negative 20, and plug it into the first derivative. So let's say negative 30. So if you plug negative 30 into the first derivative, you get negative 30 squared minus 400 is a positive number. If the derivative is positive, that means the function is increasing on this interval. Then we're going to pick a test point between negative 20 and 20, like let's say 0, and we're going to plug that into the first derivative. So f prime of 0 is going to be 0 squared minus 400, which is a negative number. If the first derivative is negative, that means the function is decreasing. Then we're going to pick a test point on the interval from 20 to infinity, like let's say 30, and we're going to plug it into the first derivative. So f prime of 30 is going to be 30 squared minus 400, which is a positive number. If the first derivative is positive, the function is increasing. So we figured out our intervals of increasing and decreasing. At the same time, we're also going to classify these 2 points as local minimums or local maximums. So let's start with negative 20. At negative 20, here, let me change the color here for this one. Let's go with red. At negative 20, the function went from increasing to decreasing. So that is clearly a local maximum. So there is a local max here at negative 20. Then at positive 20, the function went from decreasing to increasing, which means that this is a local minimum. Now, here's the thing. We are going to be putting this together on a graph, on a coordinate grid, which means we not only need the x-coordinates, we also need the y-coordinates. To find the y-coordinates, we're going to plug negative 20 and 20 into the original function, and giving a decimal approximation is completely fine. So there is a local maximum at the point negative 20, comma, if you plug negative 20 into that derivative, you get this as its approximate y-coordinate. That's fine. Then there is a local minimum. Again, you're going to plug 20 into the original function to get its y-coordinate. So positive 20, comma, 5,333.3 is going to be your local minimum. Sorry, negative 5,333.3. So next we're going to work with the second derivative and figure out the concavity and the inflection points. So let's find our possible inflection points. Potential inflection points are going to be where the second derivative 2x is equal to 0, which gives us one potential inflection point, x equals 0. So I'm going to draw another number line, and that is going to represent the second derivative. I'm going to put my only potential inflection point 0 on this number line, and I'm going to plug test points in the intervals from negative infinity to 0 and from 0 to infinity to figure out where this function is concave up and where it is concave down. So a good test point to use between negative infinity and 0 is, let's say, negative 1. Plug negative 1 into the second derivative, you get a negative number. If the second derivative is negative, that means the function is concave down. Then a good test point to use between 0 and infinity is, let's say, 1. So f double prime of 1 is positive 2, which is a positive number. If the second derivative is positive, that means the function is concave up. Also, because concavity switched on either side of 0, 0 is an inflection point. So there is an inflection point at 0, and remember, we do need a y-coordinate that goes with this. If you plug 0 into the original function, you get 0. So 0, 0 is an inflection point. So that last slide may have seemed like a lot with the steps that are needed for this. We've actually covered through steps 1 through 6. So step number 7 is figuring out potential asymptotes. Now this is a polynomial. We don't have to worry about vertical asymptotes or horizontal asymptotes because polynomials don't have any. But we are going to have to use some limits to figure out the end behavior of this function. So for the end behavior, we're actually going to be taking the limit as x approaches infinity of the original function, and we're going to take the limit as x approaches negative infinity of f of x as well. Yes, these will come out to infinity. The question is which one. Limits as x approaches positive and negative infinity will tell us what the function is doing at extremely large and extremely small values of x. That'll tell us where the arrows are pointing on our graph. So for positive infinity, again, infinity stands for a very large positive number. The x cubed term is going to be increasing a lot faster than the x term as x gets bigger and bigger. So positive 1/3 is going to be that constant multiple. A positive number cubed is a positive number. Positive times a positive gives us a limit equal to positive infinity. So basically this means that the right arrow is going to point up. Then we're going to take the limit as x approaches negative infinity of f of x. So once again, the cubic term is going to increase a lot faster than the linear term. When you cube a negative number, it is a negative. Negative infinity times positive 1/3 is going to be negative infinity. So the left arrow is going to point down. Next, for step number 8, we need to find the x and the y intercepts. So for the y intercept, you're going to just plug 0 into the original function. So f of 0 equals 0 is your y intercept. Then for your x-intercept, you're going to take the original function and you're going to set it equal to 0 and solve for x. So for the x-intercept, we're going to take 1/3 x cubed minus 400x. We're going to set it equal to 0 and we're going to solve for x. So when you solve this for x, one of your x-intercepts is x equals 0. So, if you factor out an x out of both terms, you get 1/3 x squared minus 400 equals 0. One of your x-intercepts is x equals 0. And then if you solve 1/3 x squared minus 400 equals 0, you get two other x-intercepts. You get x equals, and again, give a decimal approximation. We're putting this on a graph. 34.6 and x equals negative 34.6. So then we're going to pull this all together into a actual graph. So what I am going to do here is I'm going to put this on a separate slide. Give me 1 second. And we're going to put all of that onto a graph. So I'm going to draw my x and my y axes, and I'm not looking for a masterpiece at all. I'm looking for whether the function is increasing and decreasing in the correct spots, whether it is concave up and down in the correct spots, and whether or not you have the correct coordinates for mins and maxes and x-intercepts and y-intercepts, etc. So let's start with the x and y intercepts. So we have the point 0, 0, which was a lot. It was an inflection point, and it was a lot of different things. Then we have 34.6 for one of our x-intercepts. And then we have negative 34.6 for the other x-intercept. Then we had a local maximum at negative 20, 5,333. Good enough. Then we had a local minimum at the point positive 20, negative 5,333. Again, good enough. Now what I'm going to do next is I'm actually going to put little notes on here about where this function is increasing and decreasing and where it is concave up and concave down. And they don't need to be large notes, but just make notes to yourself so that you know that where is this increasing and where is this decreasing. So from the last slide, we know that this function is increasing on the interval from negative infinity to negative 20. So I'm just going to indicate with a little arrow here that it is increasing. Then after negative 20, it is going to decrease until we get to positive 20. Then after positive 20, it is going to increase for the rest of the graph. Remember, it needs to cross the x-axis here at negative 34.6 and positive 34.6. And now for concavity, remember, at 0 is the only place where concavity switches. So from negative infinity to 0, it is concave down, and then at 0, it switches to concave up. The left arrow is pointing down, and the right arrow is pointing up. So when we put this all together into a graph, it will look something like this. The right arrow is going to point down. Sorry, the left arrow is going to point down, and it is going to be increasing and concave down, making sure that it crosses the x-axis here at this x-intercept. And then it is going to continue to increase and be concave down until we get to this point here at negative 20. Then after negative 20, we're going to be decreasing and still concave down until we get to 0. Then at 0, it is going to continue to decrease, but it is going to go back to concave up until it gets to positive 20. Then after 20, it is going to increase and remain concave up, crossing the x-axis at that x-intercept, and then continue to increase and concave up until we get to the right arrow here. So this is an approximation of what that graph should look like, just based on information about derivatives. So we're basically going to do the same thing for this next one. We're going to be taking this function here, 4x cubed minus x to the fourth, and we are going to be using calculus to sketch an approximate graph of this function. So what we're going to start off with is the first and the second derivative. So the first derivative, f prime of x, is going to be 12x squared minus 4x cubed. Then for the second derivative is going to be 24x and then minus 12x squared. Then I'm going to find the critical points by taking the first derivative and setting it equal to 0. We don't have to worry about where the first derivative is undefined because it is a polynomial. So I'm going to take the first derivative, 12x squared minus 4x cubed. I'm going to set it equal to 0 and solve for x. So there is a common factor here of 4x squared. So I'm going to factor that out. Gives us 3 minus x. So we have two critical points. One of them is x equals 0, and the other one is x equals 3. So then we're going to draw a number line, and that number line is going to represent the first derivative. So I'm going to label it as f prime. Positive infinity is here on the right, and then negative infinity is over here on the left. And I'm going to put each of my critical points on my number line in numeric order, starting with 0, and then we have 3. Then I'm going to pick test points in each of these 3 intervals, and I'm going to plug them into the first derivative. Doesn't matter if it's factored, unfactored, you're going to plug them into the first derivative, and all you care about is its sign. So if you plug, let's say, -1 into the first derivative, you get a positive number. If the first derivative is positive, the function is increasing. Then you're going to pick a test point between 0 and 3, let's say +1. And if you plug +1 into the first derivative, you get a positive number again, so the function is still increasing. Then pick a test point between 3 and infinity, like let's say 4, and you get a negative number. If the first derivative is negative, the function is decreasing. So let's start with the easy one. We have 3. The function went from increasing to decreasing, so there is a local maximum at x equals 3. And remember, because we're going to be putting this on a graph, we do need y-coordinates to go with this. So there is a local maximum at 3, comma, remember, to get the y-coordinate, you're going to plug it into the original function, you get 27. So 3, 27 is a local maximum. Now 0, remember, if it goes from increasing to increasing, this is neither a maximum nor a minimum. So 0 is not a local extrema. Next, we're going to jump over here to the second derivative, and we're going to set the second derivative equal to 0 to find the potential inflection points. So there is a common factor here of 12x. So I'm going to factor 12x out of both terms, and that gives us 2 minus x equals 0. And then I'm going to solve for x, gives us 2 potential inflection points, x equals 0 and x equals 2. Then I'm going to draw another number line, this time to represent the second derivative, so negative infinity over here, positive infinity over here, and this is going to be f double prime. And I'm going to put each of my 2 inflection points on my number line. So I have 0 on this side and then 2 on this side. And I'm going to be picking test points in each of these 3 intervals, and I'm going to plug them into the second derivative to figure out where the function is concave up and concave down. So good test point between negative infinity and 0 is, let's say, -1. Plug -1 into the second derivative and you get a negative number. If the second derivative is negative, the function is concave down. Then pick a test point between 0 and 2, let's say +1. Plug +1 into the second derivative, you get a positive number. If the second derivative is positive, the function is concave up. Then plug a test point between 2 and infinity, like let's say 3, into the second derivative. F double prime of 3 is a negative number, so it is back to concave down. So we have a couple of inflection points. Remember, inflection points are where concavity switches, and concavity did switch a couple of times. So there are two inflection points. One of them is at 0, 0. And then when you plug 2 into the original function, you get a y-coordinate of 16. So 2, 16 is also an inflection point. Now, because this is a polynomial, we don't have to worry about asymptotes or anything like that, but we will have to still take limits as x approaches positive infinity and negative infinity to figure out the end behavior of the function. So we have the limit as x approaches infinity of the original function, and then the limit as x approaches negative infinity of the original function. At this point, we are done with the derivatives. We're going to be working with the original function for the rest of this. So, as x gets larger and larger, the fourth power is going to overpower all of the other terms. So this negative x to the fourth is going to pull on the end behavior a lot more, and it is going to influence the end behavior a lot more. So a positive number to the fourth power is positive, but because the leading coefficient is negative, this limit is actually equal to negative infinity. So the right arrow is actually going to point down. Then for the limit as x approaches negative infinity, again, negative infinity to the fourth power is a positive number, but because it is led with that leading coefficient of -1, this limit is also equal to negative infinity. So both arrows are actually going to point down. Then what we're going to do is we are going to find the x and the y intercepts by using the original function. So for the y-intercept, we are going to evaluate the original function at 0. So f of 0 equals 0. So 0, 0 is our y-intercept. Then for the x-intercept, we're going to take the original function for x cubed minus x to the fourth. We're going to set it equal to 0, and we're going to solve for x. So I'm going to factor out an x cubed out of both terms, leaving us with 4 minus x. Gives us two x-intercepts. One of them is 0, and the other one is 4. So then we're going to kind of pull this all together into an approximate graph. So I'm going to make a new slide here, and that is going to be our graph slide. So here we go. Let's draw our x and our y axes. Hold on one moment, technical problems. There we go. All right, so let's draw our x and our y axes. Start with our x-intercepts, which were 0, 0, and 4, 0. Then we had a local maximum at 3, 27. Let's make that 27. So 3, 27 is about right there, and that's our local maximum. And then we also had an inflection point at about 2, 16. So 16 is right about there. So 2, 16 is going to be one of our inflection points. And then both arrows are going to point down. So the left arrow is going to point down, and the right arrow is also going to point down. Now I'm going to make little notes on this about where this function is increasing and decreasing, and where it is concave up and concave down. We're going to use the information from the last slide. So this function is increasing and concave down until we get to 0. Then at 0, it is going to continue to increase and switch to concave up until we get to this point here at 2, 16. Then at 2, 16, it is going to switch to concave down and continue to increase until we get to this maximum here at 3. Then after 3, it is going to continue to decrease and still be concave down for the rest of the graph. So kind of pulling it all together, from the left arrow to x equals 0, it is going to be increasing and concave down. It'll look something like this, and feel free to exaggerate it. Then after 0, it is going to increase and be concave up. Then after 2 comma 16, it is going to then continue to increase and be concave down until we get to 3 comma 27. Then it is going to switch to decreasing, still concave down, cross the x-axis here at 4, then continue to decrease and be concave down for the rest of the graph till we join up with the right arrow. So keep in mind that this graph is very exaggerated. If you were to check your answers using a graphing calculator, it probably won't look exactly like this. Also, be very careful. While I do encourage you to check your graphs on a graphing calculator, some inflection points are not obvious. You would be able to see the inflection point at 0, 0 very quickly, and it would be very easy to see. But the inflection point at 2, 16 is pretty invisible to the naked eye just looking at the graph on a graphing calculator. So just be wary of that not all inflection points are easily visible. So that was curve sketching. If you have any questions on this, please feel free to email me, and I will see you in the next section for even more applications of derivatives. Thank you for watching, and I will see you in the next one.